Hello there and welcome to the Anik Pov channel. Find yourself a comfortable position right now, wherever you are. Perhaps lying in a warm bed, your head resting softly against a pillow, the weight of your body settling into the surface beneath you. Let your shoulders drop. Let your jaw loosen. Let the sounds of the day grow quieter, like a radio slowly being turned down, until all that remains is this voice and the vast, beautiful darkness of space stretched out before you in your mind. Picture for just a moment a place so far away that no light has ever returned from it. A place of impossible quiet and unimaginable force, sitting at the center of a galaxy like a secret the universe has kept for billions of years. We are going to travel there together, tonight, very slowly, very gently, following science and wonder as our only guides. And if these calm explorations help you rest or spark your curiosity, consider liking and subscribing. It helps others find their way here, one sleepy soul at a time. Now let us begin. A black hole is not, as many people imagine, a hole in space at all. It is something far more remarkable. It is a region of space where gravity has become so extraordinarily powerful that nothing, not matter, not light, not even the concept of escape, can exist beyond a certain invisible boundary. Think of it less like a drain and more like a presence. A place where the universe itself has bent so far inward that it has created something entirely new, something with its own rules, its own geometry, its own relationship with time. And as you lie there, breathing slowly, it is worth sitting with that image for a moment. A presence in space so intense that reality itself changes shape around it. Black holes are born from death, specifically from the deaths of massive stars. Stars many times larger than our own sun. Stars that have burned for millions or sometimes billions of years before reaching the end of their fuel. For most of a star's life, there is a beautiful balance happening deep inside it. The outward pressure of nuclear fusion, that tremendous explosive energy of hydrogen atoms fusing into helium, pushing outward against the inward pull of the star's own gravity. As long as that balance holds, the star shines. But when the fuel runs out, gravity wins, and it wins completely. When a massive star exhausts its nuclear fuel, its core collapses inward with terrifying speed. In some cases, the collapse takes less than a second. What was once a vast burning sphere of plasma suddenly implodes, and the result is an explosion called a supernova, one of the most energetic events in the known universe. The outer layers of the star are blasted outward in a brilliant flash of light and energy that can briefly outshine an entire galaxy. And at the center, if the remaining core is massive enough, what is left behind is a singularity, a point of almost unimaginably compressed matter, surrounded by the invisible boundary we call the event horizon. That boundary, the event horizon, is one of the most quietly extraordinary things in all of physics. It has no physical substance. You could not touch it or feel it as you pass through it. It is not a wall, not a membrane, not a surface in any material sense. It is simply the point of no return. The invisible line beyond which the escape velocity, the speed you would need to reach in order to pull free of gravity's grip, exceeds the speed of light. And since nothing in the universe travels faster than light, anything that crosses that boundary stays forever. The size of a black hole's event horizon is described by something called the Schwarzschild radius, named after the German physicist Karl Schwarzschild, who calculated it in 1916. Remarkably, while serving on the front lines of World War I, he solved Einstein's equations of general relativity from the trenches, and his solution described the geometry of space around a perfectly spherical, non-rotating mass. What he found was that any object, given enough compression, would have a Schwarzschild radius, a size at which it would collapse into a black hole. For our sun, that radius is about 3 kilometers. For the entire Earth, it would be less than a centimeter. To think that everything our planet is, every mountain, every ocean, every sleeping person, could theoretically be compressed into something smaller than your thumbnail, and in doing so, become one of the most powerful things in the universe. There is a region just outside the event horizon called the photon sphere, and it exists at 1.5 times the Schwarzschild radius. Here, photons, particles of light, can travel in perfect circles around the black hole, trapped in an orbit so precise that if you were positioned in just the right way, you could theoretically look straight ahead and see the back of your own head. Light curving endlessly around a point of infinite gravity, chasing itself in a perfect loop. It is one of those facts that seems almost too strange to be real, and yet it follows naturally and inevitably from the mathematics of general relativity. Let your breath slow a little more now. Feel the weight of your body against the bed, against whatever surface is holding you. You are perfectly safe, perfectly still, while in your mind we continue drifting closer to this extraordinary place. The center of a black hole, that point called the singularity, is where our current understanding of physics breaks down entirely. At the singularity, our equations produce results that make no physical sense: infinite density, infinite curvature of space-time, infinitely small volume. Physicists call this a singularity, not because they believe it is literally a point of infinite everything, but because the mathematics reaches a kind of boundary beyond which it can no longer accurately describe what is happening. It is like asking a calculator to divide by zero. The machine keeps running, but the answer it gives has no meaning in the real world. What actually exists at the center of a black hole remains, honestly and genuinely, one of the great unsolved mysteries of modern science. The concept of a black hole is not as new as many people assume. The idea that a body could be so massive that light could not escape from it was first proposed in 1783 by an English clergyman and amateur scientist named John Michell. He used Newtonian mechanics, the physics of Isaac Newton, to calculate that a star roughly 500 times the mass of the Sun, with the same average density, would have an escape velocity exceeding the speed of light. He called these hypothetical objects dark stars. 13 years later, the French mathematician Pierre-Simon Laplace reached the same conclusion independently. And then, for a long time, the idea faded, partly because scientists began to doubt whether light had mass, which Michel's calculation required. It would take Einstein's theory of relativity, a century later, to bring the concept back, with full mathematical rigor. Albert Einstein published his general theory of relativity in 1915, and it completely transformed how we understand gravity. Before Einstein, gravity was described by Newton as a force, an invisible pull acting at a distance between massive objects. Einstein showed that this was not quite right, or rather, not the deepest truth. Gravity, he revealed, is actually the curvature of space-time. Mass and energy warp the fabric of the four-dimensional universe. 3 dimensions of space, plus 1 of time. And what we experience as gravity is simply the result of objects following the straightest possible paths through that curved geometry. A planet orbits a star not because the star pulls it, but because the star curves space around itself, and the planet is simply following a straight line through curved space. It is one of the most beautiful ideas in the history of human thought. Space-time is a genuinely strange concept to sit with quietly at night. We are all so accustomed to thinking of space as the place where things exist, and time as the river that carries events along, that it requires a kind of mental softening to imagine them as aspects of a single, flexible, four-dimensional fabric. But they are. Your position in time is just as much a coordinate as your position in space. And near a black hole, that fabric is so severely warped that the coordinates of space and time effectively swap roles. Inside the event horizon, moving toward the singularity is not moving through space. It is moving through time. The future, in some profound sense, literally points inward. One of the most wonderful and deeply disorienting predictions of general relativity is that time does not pass at the same rate everywhere. The stronger the gravitational field, the slower time flows. This is called gravitational time dilation, and it is not a theoretical abstraction. It is real, it is measurable, and it matters in practical ways. The GPS satellites orbiting Earth experience slightly weaker gravity than we do on the surface, which means their clocks run very slightly faster. Engineers must account for this precisely, or the GPS system would accumulate errors of kilometers per day. Near a black hole, this effect becomes extreme beyond all normal comprehension. Imagine hovering just above the event horizon of a black hole, not crossing it, just hovering nearby. You would need an almost incomprehensible amount of thrust to remain stationary there. But let us imagine you could. An observer watching you from far away would see your clock running extraordinarily slowly. A few minutes of your time might correspond to thousands of years of their time. If you could hold up a clock and they could somehow read it, it would appear to them nearly frozen, ticking with agonizing slowness. And from your perspective, The entire history of the distant universe would seem to be racing by at tremendous speed. It is the same physical reality, experienced by two different observers in ways that are almost incompatible. Let your thoughts drift gently here, like clouds that have no particular place to be. You do not need to hold on to every detail. Just let the ideas wash over you, like soft waves carrying you a little further into rest with each one. The most famous thought experiment involving a person falling into a black hole is called spaghettification, and despite its slightly absurd name, it describes something real and profound. It comes from the tidal forces near a black hole, the fact that gravity is stronger the closer you are to the source, meaning that if you were falling feet first toward a black hole, the gravitational pull on your feet would be significantly greater than the pull on your head. This difference in force across the length of your body would stretch you, quite literally, into a long, thin strand, like a piece of cosmic spaghetti. The same process that stretches pasta stretches matter, because matter is matter, subject to the same forces composed of the same particles. Whether spaghettification would happen quickly or slowly depends entirely on the size of the black hole. For a stellar mass black hole, one that formed from a single dying star and has a mass of perhaps 10 to 20 times our Sun, the tidal forces are so extreme that spaghettification would begin well outside the event horizon. You would be stretched to pieces long before you reach the point of no return. But for a supermassive black hole, one with millions or billions of times the mass of the Sun, the event horizon is so large and the tidal forces at that distance are so relatively gentle that you might cross the event horizon without feeling anything unusual at all. The mathematics of scale works in a surprisingly quiet way here. Supermassive black holes are thought to exist at the centers of nearly all large galaxies in the observable universe, including our own. At the center of the Milky Way, roughly 26,000 light-years from where you are lying right now, there is a supermassive black hole called Sagittarius A star. It has a mass of about 4 million times that of our Sun, and yet, compared to the most massive black holes we have discovered, it is almost modest. Some black holes contain the mass of tens of billions of suns. The numbers become so large that they lose their grip on ordinary intuition, and all you can do is let them sit there in the mind, immense and quiet as deep water. In April 2019, humanity achieved something that had once seemed impossible. The Event Horizon Telescope, actually a global network of radio telescopes spread across multiple continents, working together as a single Earth-sized instrument, captured the first direct image of a black hole's shadow. The black hole in question was at the center of a galaxy called Messier 87, about 55 million light-years away. It has a mass of 6.5 billion suns. The image that emerged from months of data processing was fuzzy and orange-glowing, a bright ring of superheated gas surrounding a dark central region, the shadow cast by the event horizon. It was the first time human eyes had ever seen something that was, until that moment, entirely theoretical. The image was released to the world, and people wept. Then in 2022, the same team released an image of Sagittarius A star, the black hole at the center of our own Milky Way. This was technically harder to image than Messier 87, despite being far closer, because the gas and dust near our galaxy's center creates a kind of cosmic fog, and because our black hole is smaller and changes more rapidly. But the image came through, another glowing ring, another shadow, another confirmation that these extraordinary objects are real, physical, present. There is a black hole at the heart of our galaxy, and we have photographed it. As you rest there, breathing slowly, consider for a moment how strange it is that the center of our galaxy, the place around which every star in the Milky Way orbits, however distantly, is one of the most extreme environments in the universe. Most of the time it is sleeping, relatively speaking, but Sagittarius A star was not always quiet. Evidence suggests that a few million years ago, it was far more active, releasing tremendous jets of energy. The remnants of this activity, called the Fermi bubbles, are enormous lobes of high-energy gas extending above and below the plane of our galaxy for tens of thousands of light-years. We are living in a galaxy that was once lit from within. Surrounding a black hole that is actively consuming material is something called an accretion disk. This is not a solid ring, but a swirling region of gas, dust, plasma, and torn-apart matter, heated by friction and compression to temperatures of millions of degrees, glowing with fierce radiation across the entire electromagnetic spectrum. From visible light to X-rays, an accretion disk blazes with energy. And because the material in the disk is moving in a rotating flow, dragged along by the black hole's gravity and the momentum of its own spiral inward, the inner edge of the disk moves at an appreciable fraction of the speed of light. It is one of the most violent, energetic environments in the universe, and it is also, viewed through the mathematics of gravity's lensing, extraordinarily beautiful. The light from an accretion disk does not travel in straight lines near a black hole. Gravity bends it, curves it, loops it around. If you were to watch an accretion disk from a safe distance, you would see not only the front of the disk, but also appearing above and below the black hole's shadow, a warped image of the back of the disk light that is curved over the top and under the bottom of the black hole and arrived at your eyes from unexpected directions. The entire disk seems to wrap around the shadow, like an orange halo both facing you and curling behind. This is not an optical illusion or an artistic rendering. It is what the actual geometry of space demands. Some black holes spin. In fact, most black holes are believed to spin because the stars that form them are spinning, and when they collapse, angular momentum, the property of rotation, is conserved and concentrated. A spinning black hole is described by what physicists call the Kerr metric, after the New Zealand mathematician Roy Kerr, who derived the solution in 1963. A Kerr black hole is different from a non-spinning one in several important ways. It drags space-time around with it as it rotates, a phenomenon called frame dragging, or more formally, the lens-thirring effect. The very fabric of space is pulled along in the direction of the black hole's spin, like water swirling around a drain, but at a cosmic scale. The region of extreme frame dragging around a spinning black hole is called the ergosphere. It exists outside the event horizon, and it has a strange and wonderful property. Within the ergosphere, it is physically impossible to remain stationary. The rotation of space-time is so intense that even light traveling against the direction of rotation is swept along. You would be carried. And because the ergosphere is outside the event horizon, it is possible, in principle, to enter the ergosphere and escape again. This is the foundation of a theoretical energy extraction process called the Penrose process, proposed by physicist Roger Penrose in 1971, a method by which, in principle, one could extract rotational energy from a spinning black hole. The black hole's spin would gradually decrease, its energy transferred outward. Let the muscles in your face relax a little more now. Let your eyelids be heavy. You are doing wonderfully. Just resting and listening, while the universe quietly explains itself around you. What would it actually feel like to fall into a black hole? This is the question that draws so many people in, and the answer depends, as we have touched on gently, on the size of the black hole in question. Let us consider the supermassive case because it is the more survivable scenario, at least for a short while. If you were to fall freely toward a supermassive black hole, one of those giants with billions of solar masses, you would not feel anything dramatically different as you cross the event horizon. You are in free fall. Free fall feels locally like weightlessness. There is no jolt, no sensation of crossing a threshold, no alarm in the fabric of your experience. The universe outside might look slightly unusual. Light from behind you would be blue-shifted, bent, gathering at the edges of your view, but you would feel fine. And this is one of the most philosophically interesting aspects of the event horizon. It is not a place of destruction in any immediate physical sense. It is a place of no return. You could cross it without knowing, without feeling, without any instrument at your disposal at giving you a clear signal that the moment had passed. The event horizon is a global property of space-time, not a local one. It is defined by what will happen in your future, not by what is happening to you right now. You are inside the point of no return, only in the sense that every path you could ever take from now on leads to the singularity. But in the immediate present, everything feels ordinary. This fact, that the event horizon can be crossed without any immediate physical drama, has troubled and fascinated physicists for a long time. It creates a paradox. From the perspective of someone watching you fall in from far away, they will never actually see you cross. Because of gravitational time dilation, your image would appear to slow down, redshift, and freeze asymptotically at the event horizon, never quite arriving. The light from your last moment before crossing would be stretched and delayed, trickling out over vast stretches of time. To the distant observer, you would appear to hover at the edge forever, growing dimmer and redder until you faded from view. But you, in your own experience, would cross and continue falling. This apparent contradiction, you cross but the observer never sees you cross, is not a paradox in the sense of being a logical contradiction. It is a consequence of the fact that there is no universal now in relativity. Different observers can have genuinely different, equally valid accounts of the sequence of events because the concepts of simultaneous and at the same time lose their absolute meaning in curved space-time. Reality is not single-threaded. It does not have one definitive timeline shared by all observers. It is more like a fabric that can be stretched and twisted, with different parts of it experiencing duration at different rates. One of the deepest puzzles in modern physics, arising directly from black holes, is what is known as the information paradox. It begins with Stephen Hawking's discovery in 1974 that black holes are not entirely black. They emit a faint form of thermal radiation, now called Hawking radiation, that arises from quantum effects near the event horizon. This radiation carries energy away from the black hole, and over an unimaginably long period of time, it causes the black hole to slowly evaporate. Smaller black holes evaporate faster. Larger ones take almost incomprehensible lengths of time. A stellar mass black hole might take 10 to the power of 67 years to evaporate, a number so vastly larger than the current age of the universe that it barely has meaning. But eventually, in principle, the black hole would be gone. And here is where the puzzle deepens. The quantum mechanical principle of unitarity holds that information. The precise description of a physical system, the complete record of what every particle is and what it is doing, is never truly lost. It can be transformed, scrambled beyond recognition, hidden in extraordinarily complex patterns, but it should, in principle, always be recoverable. However, Hawking radiation appears to be purely thermal, random, carrying no information about what fell into the black hole. If the black hole evaporates completely, and all that remains is featureless radiation, then the information about everything that ever fell in seems to have been permanently destroyed. This conflicts with quantum mechanics at a fundamental level. Stephen Hawking spent decades working on this problem and changed his position on it more than once. He initially believed information was genuinely lost. Later, he came to believe it was not, that it must somehow be preserved in subtle correlations within the Hawking radiation, or encoded in some final remnant, or released in some other way we do not yet understand. The information paradox remains one of the most active and contentious debates in theoretical physics, touching the foundations of quantum mechanics, general relativity, thermodynamics, and our understanding of what information itself really is. Let your breathing continue, slow and easy. There is nowhere to be, nothing to do, just this quiet, gentle drift through some of the deepest ideas human beings have ever had. Hawking radiation, despite being named for one person, was actually developed through a convergence of ideas from several physicists. Stephen Hawking, Jacob Bekenstein, and others contributed to what became a surprising and beautiful result, that black holes have a temperature, something that absorbs everything, that is defined by the impossibility of escape, that seems utterly cold and dark, has a temperature. For a black hole of typical stellar mass, the temperature is almost unmeasurably small, far colder than the cosmic microwave background radiation that permeates all of space. But it is not zero, and the mathematics that produces it is some of the most elegant in all of physics. Bekenstein had proposed earlier that black holes must have entropy, a measure of disorder or missing information, proportional to the area of their event horizon. At first, this seems strange. Entropy is a thermodynamic concept, usually associated with the distribution of energy among particles in a system. What does it mean for a black hole, which seems to have no internal microstructure accessible to outside observation, to have entropy? But Bekenstein's argument was compelling and careful, and when Hawking's calculation confirmed that black holes have temperature, the connection to thermodynamics became undeniable. Black holes obey all four laws of thermodynamics. They have temperature, entropy, and they evolve in ways consistent with thermodynamic principles. The universe is more unified than it first appears. The entropy of a black hole is encoded in the area of its event horizon, not its volume. This observation, led to one of the most startling ideas in modern theoretical physics, the holographic principle. Proposed in the 1990s by Gerard T. Hooft and later developed by Leonard Susskind and Juan Maldacena, the holographic principle suggests that all the information needed to describe the physics inside a volume of space is encoded on its boundary, on its two-dimensional surface, rather than in the three-dimensional interior. In other words, the universe might be, in some deep and mathematical sense, a hologram. The three-dimensional reality we experience might be a projection of information stored on a lower dimensional surface. This is not science fiction. It is a serious and mathematically supported idea that has generated thousands of research papers. Maldaena's specific version of this idea, called the ADS-CFT correspondence, published in 1997, is one of the most cited papers in the history of physics. It posits a precise mathematical duality between a theory of gravity in a certain type of curved space and a quantum field theory living on the boundary of that space, with no gravity. The two descriptions are equivalent. You can translate any statement in one language into a statement in the other, and this duality has been used to solve otherwise intractable problems in both quantum field theory and gravity. Black holes in the interior become specific states in the boundary theory. The event horizon corresponds to something thermal in the quantum field theory. The translation works and it keeps working, and this gives physicists confidence that the holographic principle is pointing at something real and deep about the nature of reality. Some physicists believe that what we call a singularity, that point of infinite density at the center of a black hole, is actually an artifact of our incomplete theory, a place where general relativity, which is a classical theory and does not incorporate quantum mechanics, breaks down and gives nonsensical answers. If we had a complete theory of quantum gravity, one that unified general relativity with quantum mechanics, we might find that singularities simply do not exist, that the extreme compression produces something exotic but finite, perhaps a Planck scale structure of quantum geometry, rather than a true infinity. Loop quantum gravity and string theory, the two major approaches to quantum gravity, both suggest in different ways that singularities are resolved at the Planck scale. The Planck scale is the smallest meaningful length, energy, and time in physics, the scale at which quantum gravitational effects become dominant. The Planck length is about 10 to the power of negative 35 meters, which is almost incomprehensibly small. By comparison, a proton is about 10 to the negative 15 meters across, which means the Planck length is 20 orders of magnitude smaller than a proton. At that scale, the smooth geometry of space-time that general relativity assumes is thought to dissolve into something grainy, foamy, discrete, quantum space-time. What happens there, what the true microscopic nature of a black hole's interior is, remains beyond the reach of any theory we have currently confirmed. Your body is heavy now, perhaps, settled into its resting place. The thoughts about infinity and quantum foam and holographic principles are becoming soft, like words heard from the next room, present but gentle, not demanding anything of you. Beyond the singularity question, physicists have proposed various exotic alternatives to classical black hole interiors. One is the concept of a firewall. Proposed in 2012 by Ahmed Al-Maheri, Donald Maroff, Joseph Polchinski, and James Sully, in a paper often called the AMPS paper. They argued that if the Hawking radiation from a black hole truly carries information, if it is entangled with the quantum state of what fell into the black hole as quantum mechanics demands, then the event horizon itself cannot be a smooth, featureless place. There must be a wall of intense, energetic radiation at the event horizon, a firewall that would immediately destroy anything falling through. This directly contradicts the gentle, drama-free crossing that general relativity predicts. The AMPS argument set off a fierce debate among physicists that continues today, because both sides of it are supported by seemingly solid principles. Another exotic proposal is that of the Planck star, put forward by physicist Carlo Rovelli. In this picture, a black hole does not collapse to a singularity at all. Instead, quantum gravitational pressure halts the collapse at the Planck scale, creating an incredibly dense but finite object, a Planck star, that then slowly expands, the whole process taking an extremely long time as measured by an outside observer, but very short as measured from the inside. Eventually, the black hole would release all its stored information as the Planck star bounces back outward. This is an elegant idea, though it remains speculative and contested. Wormholes, those romantic shortcuts through space-time beloved by science fiction, are actually connected to black holes in a deep mathematical way. The Schwarzschild solution that describes a non-rotating black hole includes, if you extend it fully, something called an Einstein-Rosen bridge, first described by Einstein and Nathan Rosen in 1935. This bridge connects two separate regions of space-time, essentially two universes or two distant parts of the same universe, through the black hole's interior. It is a wormhole. However, the Einstein-Rosen bridge of a classical Schwarzschild black hole is not traversable. It appears and closes faster than light could traverse it. You could not use it as a shortcut. But theorists have proposed the existence of traversable wormholes stabilized by something called exotic matter with negative energy density, which would push space-time apart rather than pulling it together. We have no confirmed evidence that exotic matter in the required quantities exists in nature. Tiny amounts of negative energy have been observed in quantum systems, in phenomena like the Casimir effect. But scaling this up to stabilize a traversable wormhole is an enormous and probably unreachable challenge. Still, the mathematics allows it. General relativity does not forbid traversable wormholes. It simply requires conditions we have never observed. A beautiful and more recent idea emerging from the study of the information paradox suggests a deep connection between wormholes and quantum entanglement. Juan Maldacena and Leonard Susskind proposed in 2013 what is now sometimes summarized by the slogan ER equals EPRA, where ER refers to Einstein-Rosen bridges, and EPR refers to the Einstein-Podolsky-Rosen paper of 1935 that first described quantum entanglement. The suggestion is that two entangled particles are in some sense connected by a microscopic wormhole. That entanglement and geometry are not separate phenomena but aspects of the same underlying reality. If this is correct, then quantum entanglement, that spooky connection Einstein famously distrusted, is not just a correlation between distant particles but literally a geometric connection in space-time. The universe is more connected and more strange than it appears from the outside. The largest black holes ever discovered are called ultramassive black holes, and they challenge our understanding of how black holes grow. One of the most extreme examples is a black hole at the center of the galaxy, Holm 15A, estimated to have a mass of about 40 billion suns. Its event horizon is larger than our entire solar system, larger than the distance from the Sun to Neptune, many times over. The idea that an object of that scale, that mass, could exist in nature is one of those facts that resists being fully held in the mind. You can say the words, you can write the numbers, but the reality is so far beyond ordinary scale that it simply exists as an abstraction, hovering quietly in the space between knowing and truly understanding. Some of the most luminous objects in the observable universe are powered by black holes. Quasars, quasi-stellar objects, are the extremely bright, extremely distant cores of ancient galaxies, blazing with energy produced by matter falling into supermassive black holes at prodigious rates. A quasar can outshine its entire host galaxy, the combined light of hundreds of billions of stars, by a factor of 100 or more, and yet the energy source is a region only a few light hours across, roughly the size of our solar system. The most luminous quasar known, called JO 529-4351, is estimated to shine with the luminosity of 500 trillion suns. It is powered by a black hole consuming about 370 solar masses of material every single year. It may seem that black holes only devour and destroy, but they also, in a profound and important way, create. Galaxies and their central black holes grow together, influencing each other over billions of years. When a supermassive black hole is actively feeding, the jets of energy it releases, enormous columns of plasma, accelerated to near light speed by magnetic fields and launched perpendicular to the accretion disk, can heat the surrounding gas in the galaxy, preventing it from cooling and collapsing into new stars. This mechanism is thought to regulate star formation in large galaxies, preventing them from producing stars far more rapidly than they actually do. Black holes are not merely consumers, they are architects, shaping the structure and evolution of the galaxies that surround them. Breathe slowly, let the images settle, let the words become soft. The galaxies are doing their slow cosmic work far away, and you are here, warm and resting, with nothing asked of you tonight. A quiet mystery called the M-sigma relation reveals a striking connection between a galaxy and its central black hole. The mass of the central black hole appears to be tightly correlated with the velocity dispersion of stars in the galaxy's central bulge, the speed at which stars are moving in the inner region of the galaxy, which reflects the depth of the gravitational potential there. More massive bulges have more massive black holes in a very precise way. This relation holds across an enormous range of black hole masses and galaxy sizes, suggesting that black holes and their host galaxies co-evolve, that they grow together, influencing each other through feedback mechanisms over cosmological time. How this relationship is established and maintained is one of the fascinating open questions of modern astrophysics. Neutron stars are the smaller cousins of black holes, objects that form from stellar core collapses when the mass is not quite sufficient to create a black hole. A neutron star is a sphere of almost pure neutrons, the result of gravity compressing protons and electrons together until they merge into neutrons, roughly 12 to 13 kilometers across, but containing more mass than our Sun. Their density is almost incomprehensible. A teaspoon of neutron star material would weigh about 10 million tons on Earth, and yet, precisely because they are not quite massive enough to collapse further, they hold themselves up against gravity through a quantum mechanical effect called neutron degeneracy pressure, the resistance of neutrons to being squeezed into the same quantum state. Add enough mass to a neutron star and even this resistance fails and a black hole is born. The boundary between a neutron star and a black hole, the maximum mass a neutron star can have before collapsing, is called the Tolman-Oppenheimer-Volkoff limit, and determining its precise value is an active area of research. It depends on the equation of state of dense nuclear matter, which is still not fully understood. Current estimates place it somewhere between roughly 2 and 3 solar masses. Neutron stars more massive than this would collapse into black holes. And in 2017, gravitational wave observatories detected the merger of 2 neutron stars, a collision that produced both gravitational waves and a brilliant flash of light observed across the electromagnetic spectrum. In the aftermath of that collision, the merged object may have briefly been the densest thing in the universe before collapsing into a black hole. Gravitational waves, those ripples in the fabric of space-time predicted by Einstein in 1916 and detected for the first time in 2015, have opened an entirely new way of observing black holes. The first detection, by the LIGO observatories in the United States, was of gravitational waves produced by the merger of 2 black holes, roughly 30 and 36 solar masses in size, about 1.5 billion light-years away. As they spiraled together and merged, they briefly radiated more power in gravitational waves than all the stars in the observable universe combined are radiating as light. The entire event, the inspiral, the merger, the ringdown, lasted a fraction of a second in the most energetic phase, and the signal that arrived at Earth after traveling 1.5 billion light-years was a tiny ripple, smaller than 1/10,000th the diameter of a proton, and yet LIGO detected it. Since that first detection in September 2015, gravitational wave observatories have detected dozens of black hole mergers, as well as neutron star mergers and mixed collisions. Each detection is a new piece of information, a new data point in the emerging field of gravitational wave astronomy. We are learning about the mass distribution of black holes, the rate at which they merge, the populations of black holes in galaxies near and far. A new observational window on the universe, invisible to light but accessible through the trembling of space-time itself, has opened in our lifetime. This is not history. This is now. Primordial black holes are a hypothetical class of black holes that would have formed not from stellar collapse but from the extreme density fluctuations of the very early universe in the moments after the Big Bang. In those first fractions of a second, the universe was so hot and so dense that regions of slightly higher density could have collapsed into black holes directly, without going through the stellar life cycle at all. These primordial black holes could range enormously in mass, from tiny subatomic black holes that would have evaporated almost instantly, to much larger ones that might persist today. Some physicists have proposed that primordial black holes of a certain mass, range around the mass of an asteroid, could constitute some or all of the dark matter that makes up about 27% of the universe's mass energy content. Dark matter is one of the great mysteries of modern cosmology. We know it exists because of its gravitational effects. on the rotation curves of galaxies, on the bending of light in galaxy clusters, on the large-scale structure of the universe. But we do not know what it is. It does not emit, absorb, or reflect light. It does not interact with ordinary matter through any force except gravity. It is invisible in every electromagnetic wavelength, and it outweighs all the ordinary matter in the universe by a factor of about 5. Some of it might be primordial black holes. Most physicists believe it is probably something else, a yet undiscovered fundamental particle. But the primordial black hole hypothesis remains alive, constrained but not ruled out. A fascinating possibility, waiting for the right observation to confirm or exclude it. Let your awareness soften now, like a light dimming gently in a room you are leaving behind. The ideas are still there, floating quietly, doing no harm. Just facts about the universe, held loosely, like fireflies in open hands. There is a phenomenon called a tidal disruption event that occurs when a star wanders too close to a supermassive black hole and is torn apart by tidal forces. As the star approaches, the difference in gravitational force between its near side and far side grows until the star cannot hold itself together. It is shredded, its material forming a long looping stream that partly falls into the black hole and partly escapes. The infalling portion settling into an accretion disk and briefly blazing with energy as the sudden influx of material is consumed. These events can be detected from enormous distances because of the powerful flash of radiation they produce. Astronomers have cataloged many tidal disruption events, each one the spectacular death of an entire star, a star that had existed for millions or billions of years, in an encounter lasting only weeks to months. Some tidal disruption events produce what are called relativistic jets, narrow focus beams of plasma and radiation launched outward at nearly the speed of light along the black hole's rotational axis. When such a jet happens to point directly at Earth, we see an extraordinarily brilliant flash, sometimes visible across billions of light years. These jetted tidal disruption events are among the brightest transient events in the observable universe. One such event, catalogued as AT2022 CMC, was detected in 2022 and produced a jet pointing almost directly at Earth, making it visible to gamma-ray and radio observatories. It represented the death of a star in a galaxy 8 billion light-years away, a star that died before Earth existed, whose ending only now reached us. One of the more counterintuitive aspects of black hole physics involves what happens when you throw something into a black hole. From the outside, you might expect the black hole's mass to simply increase. And it does. The total mass of the black hole grows by the equivalent of the mass energy of whatever fell in. But this simple description hides a deeper complexity. According to quantum mechanics, the state of every particle that fell into the black hole should be, in principle, preserved somewhere, not lost. And according to the holographic principle, all of that information should be encoded on the event horizon, the two-dimensional surface of the black hole, in a way that is, at least in principle, recoverable. The black hole is not a tomb. It is an archive. Impossibly dense, impossibly scrambled, but an archive nonetheless. The concept of black hole complementarity, proposed by Leonard Susskind and others in the 1990s, offers one way to reconcile the contradictory descriptions of what happens at the event horizon. From the outside, an infalling observer appears to burn at the event horizon. The information they carry is absorbed and scrambled by a hot membrane of quantum degrees of freedom and eventually re-emitted as Hawking radiation. From the inside, the same observer crosses smoothly and continues falling. Both descriptions are correct, but no single observer can verify both simultaneously, because the two descriptions apply to regions of space-time that cannot communicate with each other. The principle of complementarity says that quantum mechanics does not require consistency between observations that cannot be compared, because no observer can be in two places at once. Reality depends in a subtle and unsettling way on who is looking. The concept of an apparent horizon is subtly different from an event horizon, and the distinction matters in ways that are not always appreciated. An event horizon is defined globally. It is the boundary of the region from which light cannot escape to infinity, and determining where it lies requires knowing the entire future history of the space-time. An apparent horizon, by contrast, is locally defined. It is the outermost surface where light rays directed outward are still being pulled inward. In dynamical situations, like the formation of a black hole or a merger, The apparent horizon and event horizon can be in different places. The apparent horizon is what numerical relativity simulations track because it is locally computable. The event horizon, in a deep sense, exists only in retrospect. Stellar mass black holes, the smaller, more common variety formed from individual dying stars, are not easy to detect in isolation because they emit no light of their own. The way astronomers typically find them is through their effects on companion stars in binary systems. When a black hole is orbiting closely with a normal star, it can pull gas from the star's outer envelope. This gas forms an accretion disk as it spirals in, and the disk glows brilliantly in X-rays. These X-ray binary systems are the clearest observable evidence of stellar mass black holes in our galaxy. Cygnus X1, one of the first suspected black holes ever identified and one of the most studied, is such a system. A black hole of about 21 solar masses in a tight orbit with a blue supergiant star about 6,100 light-years away. There may be 100 million or more stellar mass black holes in the Milky Way alone. The vast majority are invisible, floating quietly in the darkness between stars, betraying themselves only by the faint gravitational lensing of background starlight or the chance proximity of a companion star. Our galaxy is filled with these quiet presences, the collapsed remains of stars that burned and died long before our sun was born. They are not threats, not dangers. They are simply there, part of the structure of our galaxy, part of the long, slow story of matter, transforming from one form to another across billions of years. Let the thought of all that quiet darkness settle over you like a soft blanket. The darkness between the stars is not empty. It is full of history, full of the compressed remains of ancient suns. And you, lying here, are made of the lighter elements produced by those same ancient stars. You carry stellar history in your own atoms. This brings us to one of the most beautiful and frequently repeated truths in all of astronomy, the fact that the atoms in your body were forged in the cores of stars. The carbon in your cells, the oxygen you breathe, the iron in your blood, none of it was present at the Big Bang. The Big Bang produced mostly hydrogen and helium, with a little lithium. Everything heavier was synthesized later, in the nuclear furnaces of stars, or in the violent explosions of supernovae, or in the merger of neutron stars. When a massive star dies in a supernova, it scatters these heavier elements across the galaxy. They drift through space, eventually becoming part of new nebulae, new stars, new planets. Some of them, after billions of years of stellar generations, became you. The boundary between you and the cosmos is far thinner than it appears. Black holes do not, despite popular misconception, roam through the galaxy, eating everything in their path. A black hole is gravitationally powerful only within a relatively small region around it. A stellar mass black hole has roughly the same gravitational influence at a distance as a star of the same mass would have. If our sun were magically replaced by a black hole of identical mass, Earth would continue orbiting exactly as before, not pulled in, not destroyed. The planets would keep their courses. The solar system would become cold and dark, but it would retain its shape. It is only when you get very close to a black hole, within a few times the Schwarzschild radius, that the extreme differences from ordinary gravity begin to manifest. The speed of light as a cosmic speed limit is central to understanding what makes black holes special. In general relativity, it is more precisely the case that light travels along what are called null geodesics, the straightest possible paths through spacetime, the paths that experience zero proper time. Massive particles travel along time-like geodesics, paths through spacetime that are slightly curved relative to null geodesics. The event horizon is, in precise terms, the boundary where all future-pointing geodesics, both null and time-like, point toward the singularity. It is not that you would need to go faster than light to escape. It is that there are no outward-pointing paths available at all. Every direction, every possible future leads inward. The term black hole itself was popularized by the physicist John Archibald Wheeler in 1967, though the term may have been coined slightly earlier by someone else in Wheeler's presence. Accounts vary. Before this, physicists used the term gravitationally completely collapsed object, which accurately describes the physics but lacks a certain dramatic efficiency. Wheeler had a gift for naming things memorably. He also gave us the terms wormhole and quantum foam. The name black hole caught on immediately and has been the standard terminology ever since. Wheeler was also a pivotal figure in developing our understanding of nuclear physics and general relativity, and he trained a remarkable generation of physicists, including Kip Thorne, who would later win the Nobel Prize for the detection of gravitational waves. Roger Penrose, who shared the 2020 Nobel Prize in Physics for his work on black holes, proved in 1965 that the formation of singularities inside black holes is not an artifact of perfect mathematical symmetry. It is a general and unavoidable consequence of general relativity and reasonable physical assumptions. His singularity theorems showed that once a trapped surface forms, once a region of space appears from which light cannot escape, a singularity is mathematically inevitable. There is no way to arrange the matter cleverly or asymmetrically enough to avoid it. The theorems are elegant and general, and they apply under very broad conditions with minimal assumptions about the nature of matter. They represent one of the landmarks of 20th century mathematical physics. Stephen Hawking extended Penrose's work to the Big Bang, showing that if general relativity holds throughout cosmic history, then the universe itself began in a singularity, a point of infinite density from which everything expanded. The Big Bang singularity and the singularity at the center of a black hole are mathematically similar, arising from the same theorems, though the Big Bang singularity is a boundary of space-time in the past rather than a gravitational collapse in the future. This parallel has long intrigued cosmologists and has driven many attempts to understand both singularities within a theory of quantum gravity that might resolve them both. There is a quiet beauty in how the mathematics of general relativity contains implicit within it all of these extraordinary phenomena. Einstein was not looking for black holes when he wrote down his field equations. He was trying to describe gravity correctly, to replace Newton's action at a distance with a geometrical framework. But the equations contained more than he put in. They contained gravitational waves, they contained cosmological expansion, they contained black holes. All of these were there in the mathematics from the beginning, waiting to be found. Science is sometimes like that. You ask one question carefully enough and the answer comes back containing other questions, deeper rooms, longer corridors. The universe is more than it has to be. Let your thoughts become quieter still. You have traveled an enormous distance tonight, through event horizons and singularities, through the mathematics of time and the weight of infinity, and you are still here, still breathing, still at rest. Let the last few ideas come like distant music, soft and unhurried. Black holes and entropy share a profound relationship that hints at a deep unity between gravity and thermodynamics. Jacob Bekenstein's realization that a black hole's entropy is proportional to its event horizon area. Specifically, 1/4 of the area in Planck units is called the Bekenstein-Hawking entropy formula. It is one of those equations that, when physicists stare at it, gives them the feeling that they are looking at a clue to something very deep. The formula contains the gravitational constant, the speed of light, Boltzmann's constant from thermodynamics, and Planck's constant from quantum mechanics, all 4 fundamental constants of nature, gathered together in a single elegant expression. It is as if the formula is whispering that these 4 great theories, gravity, electromagnetism, thermodynamics, quantum mechanics, are secretly aspects of one unified truth, a subject known as black hole. Thermodynamics has 4 laws in direct analogy to the 4 laws of ordinary thermodynamics. The 0th law states that the surface gravity of a black hole is constant across its event horizon, analogous to the 0th law of thermodynamics, which states that a system in thermal equilibrium has a uniform temperature. The first law relates changes in mass, angular momentum, and charge of a black hole to changes in its area, analogous to conservation of energy. The second law states that the total area of a black hole's event horizon can never decrease, analogous to the second law of thermodynamics, which states that entropy never decreases in a closed system. And the third law states that the surface gravity of a black hole cannot be reduced to 0 by a finite process, analogous to the thermodynamic impossibility of reaching absolute 0. The fact that the area of an event horizon cannot decrease has a beautiful consequence in the context of black hole mergers. When 2 black holes merge, the area of the resulting event horizon is at least as large as the sum of the areas of the 2 original event horizons. This area increase theorem was proved by Hawking in 1971, and it was confirmed directly by the gravitational wave observations of 2015. After the merger of the two black holes detected by LIGO, the area of the final black hole's event horizon was greater than the combined area of the original two. It was the first direct observational confirmation of Hawking's area theorem, something beautiful from 1971, confirmed by a gravitational wave signal 1.5 billion light-years away, arriving at Earth in 2015. The universe keeps its promises. In recent years, there have been proposals for observational signatures that might distinguish different models of the black hole interior. If black holes are not classical general relativistic objects but instead something more exotic, Planck stars, fuzzballs from string theory, or objects with firewalls, there might be subtle echoes in the gravitational wave signal following a merger. The ring-down phase, as the newly merged black hole settles into a stable state, is predicted by general relativity to have a specific form. Deviations from this form, tiny echoes appearing after the main signal, might indicate that the object is not a classical black hole. Searches for these echoes in existing gravitational wave data have so far been inconclusive, but future detectors, including the space-based LISA mission planned for the 2030s, will have far greater sensitivity, and the question may be answered. String theory, one of the most ambitious attempts at a unified theory of physics, offers its own picture of black holes. In string theory, particles are not point-like objects, but tiny vibrating strings of energy, and the theory predicts a much richer structure for what lies at and near the event horizon. One proposal, called the fuzzball, suggests that what we call a black hole is actually a dense tangle of strings, occupying a region that extends all the way to what appears from outside as the event horizon. In this picture, there is no smooth, empty interior and no singularity, just a complex quantum object made of strings whose surface is the event horizon. Hawking radiation would arise from the vibrations of this string condensate, and information would be preserved in its structure. The fuzzball idea remains speculative, but it is mathematically consistent and has generated substantial research. The binary black hole systems that produce gravitational waves are often the result of two massive stars that formed together, lived their lives together, and died together over millions of years. They were stellar siblings, born from the same cloud of gas and dust, burning through their fuel at similar rates, collapsing within millions of years of each other. Then, as black holes, they continued their orbital dance, slowly losing energy to gravitational wave emission, spiraling ever closer across millions more years, until the final plunge. The merger that LIGO observed in 2015 was the culmination of a 1.5 billion-year journey, the final chapter of a story that began before our solar system existed. The gravitational wave that crossed the universe and tickled our instruments was the sound of that ending. If you could somehow survive at the edge of a black hole's accretion disk, the visual experience would be unlike anything in normal human experience. The extreme gravitational lensing would warp your view of the surrounding universe into strange shapes. Stars and galaxies bent into arcs and rings, the entire sky compressed into a bright band above and behind you, with the black hole's shadow dominating your forward view. The disk itself would glow with fierce, uneven brightness, brighter on the side approaching you, dimmer on the receding side, due to the Doppler effect of material moving at relativistic speeds. The colors would shift, blue-white and intense from the hot inner regions, redder and cooler further out. Time would be running differently for you than for observers far away. Everything would be alien, beautiful, and utterly hostile to life. The imagined journey of falling into a black hole, particularly a large one, has been simulated visually by physicists and artists using the equations of general relativity. The 2014 film Interstellar made use of some of these simulations, produced in collaboration with physicist Kip Thorne, who later won the Nobel Prize for gravitational wave detection. The visual effects team created the most physically accurate depiction of a black hole's accretion disk and gravitational lensing ever shown in a major film. The simulation produced images that surprised even the physicists involved. The accretion disk, when correctly modeled, appears to arc over the top and underneath the black hole simultaneously, creating a halo effect not widely anticipated. The results were so scientifically interesting that Thorne and colleagues published research papers based on them. As you drift now, your eyes perhaps already closed, the image of that glowing ring, light, curved impossibly around a point of infinite gravity, can sit quietly in your mind like a soft ember, not demanding anything, just there, a reminder that the universe is full of things more extraordinary than anything we could invent. The fate of our own sun is not to become a black hole. Our sun is not massive enough. When it exhausts its hydrogen fuel in about 5 billion years, it will expand into a red giant, puffing out to perhaps 100 times its current size, likely engulfing Mercury and Venus and possibly Earth. Then the outer layers will gently drift away as a planetary nebula, a beautiful glowing shell of gas illuminated by the hot remnant core. What remains will be a white dwarf, a compact, hot, dense sphere about the size of Earth, made primarily of carbon and oxygen. Without nuclear fusion, it will slowly cool over billions of years until it becomes a cold, dark object called a black dwarf. The universe, as currently understood, is not yet old enough for any white dwarf to have cooled into a true black dwarf. Every white dwarf that exists is still glowing. The most massive stars in the universe, those with perhaps 40 or more times the mass of the sun, may form black holes directly from collapse. Without the dramatic fireworks of a visible supernova, these events are called failed supernovae, or direct collapse events. In a typical supernova, the core collapses, then bounces, and the resulting shock wave drives the outer layers of the star outwards in a tremendous explosion. But for very massive stars, the shock wave may not be powerful enough to escape the intense gravity of the collapsing outer layers, and the entire star simply falls inward, vanishing from view in a fraction of a second. Astronomers have searched for and found a small number of likely direct collapse candidates, massive stars that simply disappeared, without any recorded explosion, from one observation to the next. The sound of a black hole merger, rendered as an audio signal from the gravitational wave data, is something brief and strange. It begins as a low hum, too slow to hear, gradually rising in pitch and amplitude as the two black holes spiral closer, culminating in a brief chirp, a fraction of a second of rising tone, as they merge. Then a short ringdown as the merged object settles. The entire audible portion might last less than a second, but this signal, this brief chirp crossing a billion light years, is the most energetic event astronomers have ever detected. 3 solar masses worth of energy were converted into gravitational waves in the final moments of that merger, released in roughly a tenth of a second, in a blast that momentarily exceeded the luminosity of all observable stars combined. We have been speaking tonight as though black holes are rare and distant things, but the cosmos contains more of them than it is easy to imagine. Every large galaxy has a supermassive black hole at its center. There may be tens of millions of stellar mass black holes in our galaxy alone. The observable universe contains hundreds of billions of galaxies. The number of black holes, summing them all, is a figure that staggers any attempt at intuition. They are not exceptional. They are ordinary features of the universe, the natural endpoints of enough mass compressed into small enough space, the final punctuation marks at the end of massive stars' long burning sentences. And yet, despite their number, despite our growing ability to detect them and image them and hear them, there remains so much we do not know. We do not know what singularities truly are. We do not know how information is preserved during Hawking evaporation. We do not know the microscopic structure of the event horizon. We do not know whether primordial black holes exist or whether they constitute any fraction of dark matter. We do not know whether a theory of quantum gravity will resolve the apparent contradictions or reveal something even stranger. Black holes are simultaneously the objects we understand best, through the clean precision of general relativity, and the objects that most dramatically reveal the limits of our understanding, at the boundary where quantum mechanics and gravity must somehow speak the same language and currently do not. This is the gift of science. Not just the answers it provides, but the questions it reveals. Every mystery solved opens onto deeper mysteries. Every mountain climbed reveals higher peaks. And the process of that discovery, the long, careful, collaborative work of minds across generations, is itself one of the most remarkable things in the universe. A species of upright primates living on a pale blue dot orbiting an unremarkable star has used mathematics and observation and imagination to peer into the hearts of galaxies billions of light years away, to detect the trembling of space-time from black holes merging before our planet existed, to image the shadow of a monster containing the mass of 6 billion suns. This is extraordinary. You are the product of a species capable of this, and that is something worth holding gently as you rest. The night sky above you, even if walls and weather obscure it from view right now, contains all of this. Every point of light up there is a star or a galaxy, and somewhere in nearly every galaxy there is a massive sleeping heart, a supermassive black hole around which billions of stars slowly orbit, which occasionally wakes to consume a passing star or gas cloud, flaring brilliantly for a time, before settling back into its long, quiet waiting. The universe is alive with these presences, these vast gravitational anchor points, these punctuation marks of matter's terminal compression. Let your own heartbeat slow now. Let your breathing become effortless. The images of black holes and event horizons and glowing accretion disks can drift quietly away into the soft background of a darkening mind. They will still be there in the morning or in some other quiet evening, waiting to be revisited. Science is patient. The universe is patient. There is no rush. You have traveled an extraordinary distance tonight without leaving your bed. You have considered what happens at the edge of space-time, what the word boundary means when there is no substance to mark it, what it means for time to slow and stretch and finally stop. You have held very lightly some of the deepest and most difficult ideas in all of human knowledge, and you have done it gently, without strain, letting them wash over you like warm water. The black hole at the center of our galaxy is there right now, in this moment, as you lie here 26,000 light-years away, 4 million times the mass of the sun, wrapped in its invisible horizon, slowly absorbing any gas that drifts too close, surrounded by a dense cluster of old stars orbiting in intricate gravitational choreography. It has been there for billions of years. It will be there for billions more, and somewhere much further away, those two black holes we detected merging, the ones whose gravitational wave arrived at Earth in 2015, continue their merged existence, a new and larger black hole, settling into Kerr geometry, slowly radiating its microscopic quantum whisper into the void, indifferent to time, carrying its secrets. If another video continues, let it carry you gently. And if sleep finds you now, then rest well. Good night.